Hello, everybody. Welcome to the downstream processing in biotechnology lecture. For this lecture, we will focus on the adsorption process. What is the adsorption process? Adsorption process is the surface phenomena that is used in terms of gas or liquid can be concentrated or accumulate in the surface of the solid. Adsorption is the result of the electrostatic van der Waals force or reactive or the binding force between individual atom, ion, or molecule. In adsorption, we have at least 4 types of adsorption type or interaction. Like we have like exchange, the exchange between ion, for example, physical process adsorption, chemical adsorption with the chemical reaction, and non-specific. That's right. Non-specific means there is no specific site between the solute and solid surface, something like this. Okay. In the bioprocessing, we apply adsorption process to isolate the product from the dilute fermentation mode. For example, or we utilize the cover amino acid. We use to liquidate amino acid like this, protein, antibiotic. This is the example for the biomolecule like amino acid, protein, antibiotic. We can use like the ionic chain adsorption, like also vitamin, something like this. Mostly we apply for the medical, pharmaceutical product, also the food product, something like this. And the most common use of the adsorption we can all know is activated carbon or activated charcoal. This is the most common adsorption process. We use the activated carbon. That's like for the bioprocessing, we use the activated carbon to purify citric acid. That's like we use the adsorption of organic chemical or charcoal or product polymer at the adsorbent. That's like the charcoal, the product polymer at the adsorbent to treat the wastewater. That's like to treat the wastewater. Right. In terms of adsorption, we can consider 2 terms, adsorbate and adsorbent. Adsorbate means a substance also used in terms of gas or liquid that's concentrated on the surface of adsorbent. That means the solute in terms of gas or liquid accumulate on the surface of solid. This solid means adsorbate. Adsorbent means it material to which the adsorbate by adsorbate that accumulate. This is a very important term like adsorbate, adsorbent. And this figure shows you the adsorption operation in general. That's right. In the general, right? This is the adsorbent. That's right. Adsorbent. This may be a lot of shape, a lot of size. We call it adsorbent. And this is the unbound solute. And this is the adsorbate that accumulate on the surface of on the surface of the adsorbent. That's right. And after adsorbate is attached or accumulate on the surface, and then we will separate this. That's right. We will separate it by we call it desorption. After you desorption, adsorbate or solute will remove out from the surface of the adsorbate. That's right. At least 2 steps. The first step is adsorption. The second step is desorption. We call it solid liquid separation step. The general process for the adsorption, we have at least 3 steps. That's right. We have at least 3 steps. And the first step we call it adsorption operation or contact. So you interval liquid contact with the surface of adsorbate. This is the first step. We load the solute, load the gas phase, or the liquid phase. It's maybe by ion exchange, by physical adsorption, chemical adsorption, something like this. That's the solute adsorbed to the adsorbent or solid surface. And the next step, watching. Watching step is the step to remove some residual unadsorbed base material. That's right. If we feel material, that's right, only some part or some solute that can be adsorbed or accumulate to the surface. But there are also some unadsorbed. For this step, we watching. That's like we remove some residual unadsorbed. After you remove unadsorbed material, and then you have to desorption or elution. For this case, we use some solvent, some thermal method, something like that, to remove adsorbed, That's right. And then you watching again. For this case, we remove some residual eluent. Eluent, we call this a solvent that used to remove adsorbed. That's right. And then you can regenerate the adsorbent resin, something like this, or reuse again. That's right. For this, we need to recycle. That's right. After you finish like contracting, watching, desorption, and washing again, and then you can regenerate for using the resin or adsorbent again. This is the most common the adsorption process. Okay. And also the mechanism. You can see that the mechanism for the adsorption, for this case, if the adsorbent is the porous material, we have the pore, and also the solid surface. The first one is the solid in the pore. That's right. Solid in the pore. This is the bulk solution of the solid. The fluid that's in the pore. And number two is the solid or solute accumulate on the surface. Because this is a step. This is more physical or chemical. It depends on the surface of the pore. It's like, is it the surface or active site for adsorption like this? It's also the surface is the active site for adsorption. It may be chemical reaction. It may be an exchange. It may be the specific like ligand. It may be like the biological activity. For example, like this, if the surface of the adsorbent act as the ion exchange. For this case, the resin is an ion. For this case, we call this cation exchange. That means this adsorption surface is used for exchange between cation. That's that, gas ion. Or the cation can accumulate to the surface of adsorbent, and an ion not accumulate. That's that. And this is an anion exchange, because only anion can be accumulated to the surface of the adsorbent. Okay. In conclusion, for the cation exchange, that means the surface of the adsorbent is an ion. That means only cation or the solute can accumulate. For the anion exchange, that means the surface of the adsorbent is cation. That means only anion can be accumulated to the surface. This is, for example, right, the ion exchange. That's right. The mode adsorption process utilize particulate adsorbent. And mostly we use the particulate adsorbent. It may be produced from natural or synthetic material. Synthetic material is also amorphous or crystalline structure. Physical form result is very high specific surface. It should be very high specific surface. It should be ion exchange surface. It should be chemical reaction in the surface. It's commonly the adsorbent used in bioseparation process. That's what we use. For example, right? Silica gel bed adsorbent, synthetic resin, agarose bed adsorbent, cording dextrane adsorbent. This is the common use for the bioprocess adsorbent. And the next step, we will talk about the isotherm. Isotherm, we talk about the equilibrium state. That's right. When in the adsorption process, we have two components in the liquid or gas phase and in the surface of solid. For this case, we have to know what is the concentration of solute in the liquid phase or fluid phase. What is the concentration of solute in the surface of the solid? That's right. We talk about it in terms of isotherm or adsorption isotherm. Adsorption isotherm is the relationship between concentration of solute or species in solution or in liquid or gas phase, and concentration of solute on the adsorbent surface. That's why we represented by Q and represented by C. Q is the amount of adsorbate or solute per amount of adsorbate in terms of kilogram mass adsorbate per mass of adsorbate or mass adsorbate per volume per liter of adsorbate. This is the concentration on the surface of adsorbate. And concentration in the liquid phase or in the solution is the mass of adsorbate or solute per mass of solution or mass of solute per liter of solution or per volume of the solution. That's right. In this class, we introduce you about three kinds of isotherm. That's right. In the linear term. Linear term with the Q and C is linear relationship. It's on Langmuir isotherm and Friedrich isotherm. Right. For the first one is linear isotherm. Linear isotherm means the Q is a function of C in terms of this equation, like Q equal to Kc. K is equilibrium constant. This can be determined by the experiment. As K is the dimension, the frequency is the solution volume per adsorbent mass, something like this. Linear isotherm is not common. It may approximate the other isotherm over limit length of concentration, particularly in dilute solution. That's right, dilute solution. For another term of the isotherm is Friedrich. Friedrich isotherm is expressed by Q equal to Kc power 1 by T. That's right. For this case, it's also its white space is many common. It's common used in liquid solid system. That's right. It describes a variety of antibiotics, steroid, hormone absorption. Like K and N are constant. It also can be determined from the experiment. That's like K depend on value of Q, C, and N. That's right. For this case, we can consider N. We can consider N. If N is greater than 1, this means absorption is unfavorable. Sorry, N greater than that means the absorption is favorable. That means we can separate by absorption. If N is less than 1, absorption is unfavorable. That means it's difficult to separate by absorption. That's right, absorption. For this case, if we take log of Q, that's right. Sorry, Q equal to log K C power N. That's right. This is equal to log K plus 1 over N log C. That's right. In this case, we can plot between log Q, right, log Q and log C. Like this is maybe some, sorry, it plots between log Q and log C. You get a slope 1 over N. That's right. And intercept is, sorry, like this. Okay. Okay. You plot between log C, log Q. That's a slope is 1 over N. Intercept is log K. That's right. For this case, you can determine like the N and K from the plot between log Q and log C. If you have the data of Q and C, you can determine K and N for that case. Right. The last isotherm that I talked to you is the Langmuir isotherm. Langmuir isotherm is often used to cover the absorption data of protein. Like this expression. This is we know like is the C and S. CS. C is the concentration of adsorbate in solution. Here this concentration is the solid surface. S is the concentration of, C is the concentration of adsorbate in solution. That's right. In terms of kilogram adsorbate per volume of solution. CS is the concentration of adsorbate on the surface adsorbate. That's right. This means the kilogram adsorbate per kilogram adsorbent. S is the concentration of the empty adsorption site. That's why K is constant. That means from this case, you can determine K is CS divided by C and S. And also, for that case, you can determine the total site concentration is CS part S. This is the maximum adsorption site. S total means the maximum site for adsorption. The maximum site on the surface for adsorption for the monolayer. The combination of these two equations, and then you can calculate the concentration of solute on the surface of the solid. That's right. Ks total C divided by 1 plus Kc. Okay. If we representatives concentration of Cs is Q, Q is the concentration of adsorbate on the surface of the adsorbent at equilibrium. Q0 is total, is the maximum loading of adsorbate. This corresponds to the complete monolayer coverage. This based on monolayer. One adsorbent site. It depends on the specific area of the adsorbent and molecular site. Okay, and C is equal to C. And then you can rearrange this. That's right. Q, concentration of solute on the surface of solid at equilibrium equal to maximum concentration, Q0. Kc divided by 1 plus Kc. If we divide this top and bottom by K, we get K, this cancel. K, this cancel is 1 over K. We substitute 1 over K is the Ka like this. For this we K. That's right. K, this cancel. This cancel. But it cancel, but it's 1 over K. That's right. And then you get like the 1 over K equal to Ka. You get Q equal to Q0 C divided by Ka plus C. And then you can rearrange this equation. This is the Langmuir isotope. That's right. This is the Langmuir isotope. And also you can rearrange to be the linear equation like this. This is the linear equation. For this case, you can process. For this case, you can process. You can process this 1 over C, 1 over Q. That's right. This is the linear equation. When the slope, what is slope? Slope is Ka over Q0, and intercept is 1 over Q0. That's right. If you plot between 1 over Q versus 1 over C, you can determine the Ka and Q0 with the constant. If you have the data from experiment, you can calculate Ka and Q0. Okay. If you would like to know what is the mechanism of the adsorption, you can fit your data with this equation for Langmuir. That's right. If you plot 1 over Q and 1 over C is the linear equation, okay, your data follow the Langmuir isotope. That's right. For Frederick, if you plot between log Q and log C, if your data is linear, okay, you can conclude that your isotherm, your adsorption is the Frederick adsorption. And also, if you plot Q and C is linear, it is also the linear isotope. But we have only only 3 isotopes: linear isotherm, Frederick isotherm, and Langmuir isotope. How about the Langmuir isotope? The Langmuir isotope, if C is very, very small value compared to Ka. That's right. From the previous equation, that's right. Q equal to Q0 C divided by Ka plus C. That's right. If C is very, very small compared to Ka, you can cancel this term. You can cancel the term. You get Q equal to Q0 divided by Ka plus C. You get linear isotope. Q over K is constant. This is linear isotope. And also, if K is very, very small compared to C, in this case, you can cancel this. Q0 multiplied C divided by C, you can Q, that means is the constant. That's right. If the C is very, very small compared to Ka, Langmuir isotherm is close to linear isotherm. That's right. If K is very, very small compared to concentration, Q approach to constant of Q0 is maximum adsorption. That's right, adsorption. Okay. In based on the theoretical Langmuir adsorption is applicable to system where adsorption molecule form no more than a monolayer. It's only monolayer adsorption. That's right. And the second one, each side of adsorption is equivalent in terms of adsorption energy. And the last one, there is no interaction between adjacent adsorbed molecule. For example, right? For example, we have the surface of liquid solid. That's why the molecule adsorb. That's why the first one there is no the second layer. That's why it's only this layer. There's no the second or the third layer. This is the Langmuir isotherm is only monolayer, is monolayer. That's right. There is no the second layer. And also the number three, that's right, the interaction between this molecule and this molecule. There is no interaction between this adjacent. That's right. That means only the monolayer and the molecule that's adjacent, no interaction. That's right. This is the assumption for the Langmuir isotherm. Okay. We will show you about the example. The first example, we talk about the gentamicin adsorption on carbon. We use the activated carbon for the adsorption. We have measured adsorption of antibiotic gentamicin, that's from water at pH 9.5 onto a non-ionic carbon. We find the following result. We have the concentration in solute, a solution, and concentration adsorbed to the solid surface Q, C and Q. That's right. Q and C and Q like this. Okay. The question: what adsorption isotherm fit this data? For this case, we show you only three. That's right. If you put Q and C, if Q and C is linear, okay, we can conclude that this is linear isotherm. If you put 1 over Q versus 1 over C, if it's linear, you can conclude it is the Federic linear, Federic isotherm, Federic isotherm. That's right, Federic isotherm. Okay. Sorry. If you put log Q versus log C, if you get linear graph, okay, you can conclude it Federic. And if you plot between 1 over Q versus 1 over C, if you get linear, okay, you can put like that. For this example, we can do like this. We plot the first we plot between Q and C. This is not linear. That's right. If you get the linear relationship, okay, you can conclude linear isotherm. Okay, there is no linear isotherm. And the second one, you plot between 1 over Q and 1 over C. It's not linear also. That's right. It's not Langmuir isotherm. And the last one, you plot between log Q versus log C, you get approximately linear relationship. For this case, for three linear isotherm, Langmuir isotherm, phenolic isotherm. For this example, we can conclude that it approaches phenolic isotherm. And then you can calculate the slope. The slope is 0.4116. 4116. And then you can calculate n equal to 2.44. That's right, n is greater than 1. That means your adsorption can be occur easily. And intercept is 3.56. That's right, log K. And then you can estimate K is 35.3T. And then you can express Q in terms of Q equal to Kc power 1 over n. That's right, this K. This is thing like this. Okay, this is for the first example. For the second example, let's say we talk about the adsorption of immunoglobulin G or IgG adsorption. We have 80 cubic centimeter of modified pectin will adsorb up to 7.8 multiplied 10 power minus 6 more hemoglobin G per cubic centimeter of adsorption. This absorption follow Langmuir isotherm with a constant K equal to this value, concentration. The question is what concentration in 1.2 liter of feed solution will have 90% of deck train capacity is 90% recovery. From the problem statement, that's right. We would like to achieve 90% recovery. We expect concentration, C is concentration of hemoglobin G in solution. That's right. That means the remaining solution, that's right, the remaining hemoglobin G in solution is 10%. Is equal to 0.1 CF. CF is the concentration initially. Okay. For Langmuir isotherm, you can follow like this. You know Q0 is the maximum absorption. This Q0 is maximum. And C is 0.1 CF. You know K, you substitute C, CF, K, and Q0 to Q. That's that you can express that Q is a function of CF. Okay. If we draw some absorption unit, for this absorption unit, we have the feed, we have the concentration of solute immunoglobulin G in solution. That's right. Yeah. For this case, a volume of feed solution, we assume it equal to the final volume of solution equal to 1.2 liters. And C is the final concentration after absorption. That's right. Some solute molecule is transferred to adsorb or accumulate on the surface of solid. C is the remaining solute in the solution is 0.1 cm. This we assume it in equilibrium, 0.1 cm. P is the total amount of adsorbent. In this case, it deck train is 80 cubic centimeter. And Q is the concentration of solute adsorbed on the deck train surface at equilibrium with C. QF is the concentration of HV. That's right. QF is the amount of solute or immunoglobulin G that adsorbed in the surface at the initial state. It is zero because at the initial state there is no solute adsorbed on the surface. That's right. QF is zero. And then you can apply the mass balance around the absorption unit. We consider it initial step and final step. For this case, there is no reaction. No generation, no consumption. We consider only in the initial step and final step. That means no accumulation. That's right. It should be input equal to output or initial step equal to final step for this case. Okay. The initial step we have FCF plus PQF equal to FC plus PQ. We know that QF is 0. That's right. F is 1.2 liter multiplied CF equal to F is 1.2 liter multiplied 0.1 CF. P is 80 cubic centimeter multiplied Q. That's right, multiplied Q. And then you know Q from this equation, from the Langmuir isotherm. You substitute Q into this equation. That's right. And then you can solve for CF. Because Q is a function of CF already. You substitute Q in this equation, and then you have only one value is CF, and then you can solve for CF. CF is 3.9 multiplied by 10 minus 4 mole per liter. Please notice it's mole of solute per liter of solution. That's that. Okay. Is it answer our question or not? Yes. Concentration. Okay. CF. The last example for this section, antibody recovery by adsorption. Okay. Cell-free fermentation liquid contain 8 multiplied 10 power 5 mole per liter immunoglobulin G. This is proposed to recover at least 90% of the antibody by adsorption on synthetic non-polar resin. For this case, we would like to recover 90% of immunoglobulin G from the fermentation board, that there is no cell in the fermentation board. like cell-free fermentation, that means no cell in the fermentation board. Okay. We have the initial concentration is S multiplied 10 minus 5 mole per liter. And we utilize the synthetic resin with non-polar synthetic. At equilibrium, data are correlated at Q equal to 5.5 multiplied 10 minus 5 C power 0.35. This is the equilibrium or isotherm. We know the isotherm, the relationship between Q and C at equilibrium. That's right, at equilibrium. For this case, Q is the mole of solute per cubic centimeter of adsorbent, and C also is the solute concentration is mole per liter. The question is, what minimum quantity of resin is required to treat 2 cubic meter of fermentation liquor in a single stage mixed tank? We use only one tank in the mixed absorption. Okay. For this case, the minimum quantity of resin is required when equilibrium occurs. If 90% recovery of antibiotic is adsorbed, what does it mean? 90% of immunoglobulin G in solution is transferred to the solid surface, as aqueous surface, and only 10% remain in the solution. That means the final concentration after adsorption is 10%. 100 minus 90 is 10%. It's 0.01 CF. It's 0.1. This is CF. You get this is the concentration at the final stage after extraction, after adsorption. Right. Okay. You substitute C this in the isotherm. Right. You substitute C in the isotherm, you get Q. That's right. This Q. This is in equilibrium. And then you can calculate amount of adsorbed antibody. That's right. Amount of adsorbed antibody you calculate on 90% recovery. 90% divided by 100% multiplied by CF. That's right. This is the volume of the solution. This volume of solution. This is the convert unit. You get 0.144 mole. 0.144 means amount of solute that adsorb or accumulate on the surface of solvent. For this case. Okay. This is the list of solution. This is the cubic centimeter solution. This is the unit. This is volume of solution. Volume of solution. That's right. This is mole of solute or immunoglobulin G accumulate on the surface of adsorbent equal to 0.144 mole. And then you can calculate adsorbent needs. Adsorbent needs is equal to mole of solute that adsorb on the surface divided by 9.05 multiplied by 10 power minus 7 mole per kg. What this means? This is the concentration of solute adsorbed on the surface. That's right. It's the concentration. You know concentration, you multiply by amount. That's right. You get volume of adsorbed. This is amount of adsorbed, amount of immunoglobulin G at the surface. This is the concentration of immunoglobulin G at the surface. It means mole of immunoglobulin G at the surface per volume of adsorbed. Mole, you get volume at adsorbent 0.16 cubic centimeter per cubic meter. This is the minimum quantity of resin required. That's right, minimum quantity of resin required. I will stop the lecture for this section, and we will continue for the next section on the ionic chain isotherm. Okay, thank you.